Welcome to all. So today we'll start the third lecture. Okay, the third lecture topic is elementary impact and stress wave consideration. Here we'll deep dive into the impact theory and look into the different aspects. So today we will be covering the impact phenomena, the phenomena dealing with the contact mechanics, that is when two bodies come into contact, what is their behavior, how is the stress transfer. Then moving ahead, then we will look into the penetration phenomena and perforation phenomena. And finally, we will be looking how the stress waves propagate during an impact event. So let us start the things. The impact phenomena. Here what we will do is that we will overall look into the impact phenomena, what is impact and what is the behavior of the things during the impact. So in our day-to-day life, most engineers run into the cases of impact loading. The general problem of impact is extremely complex. This is due to the inherent behavior of the materials, the contact that is occurring, the deformation that is occurring in the bodies. However, what we will do is that we will use a reasonable and useful approximations, okay, to get an estimate and to study how the bodies behave during an impact event. And what we will do is that we will try to simplify the phenomena from the first principles that we have learnt throughout our life. So let us simplify the impact analysis. Okay, what we will do is that we will come from a complex impact scenario to a useful engineering estimate. What needs to be done is that first the key factors needs to be identified. Key factor means the material properties, the behavior of the material during a high strain rate event, the deformation phenomena, the boundary conditions. Okay. After that, what we will do is that we will apply the first principles, okay, the principles of conservation of energy, the principles of conservation of momentum, and we will also make some simplifying assumptions. Okay. And combining all these things, what we will do is that we will estimate the effect of the impact from one body transfer to the another. Okay. And at the end of the day, what we will get is useful engineering estimate, maybe the deformation, maybe the stress that is being transferred, that we can use in the design process. Okay. So let us move ahead. Let us try to understand the physics of impact. Okay, what happens? Okay, so this is a very simplified approximation. Okay, whatever we have learnt in the last slide, we are now trying to categorize this thing. Okay, so what happens is that one moving object comes, okay, and it lands on the other body. Okay, so when these two bodies come into contact, this is classified as an impact. In an impact, what we will do is that we will apply the first principles, that is the principle of conservation of momentum and the principles of energy conversion. Okay, so these principles we have learnt in our first year BTech. Okay, so using this very simple equations, okay, we'll move ahead and we'll try to calculate the strain energy, the energy dissipation, okay, the other factors like friction, plastic deformation, propagation of stress waves can be approximated using all these things. Okay, so what we have done is that we have taken a very complex scenario, that is the impact between two events. We have simplified it, we are calling it as a contact when two moving bodies come into contact. Both bodies can be moving or at least one body should be moving. Okay, we applied the principle of conservation of momentum, we applied the principle of energy conversion. Okay, we estimated the strain energy in the target, we also try to estimate the energy dissipation. So these two things we can call it as the key thing. Okay, and from there we can estimate the friction, we can estimate the plastic deformation that is occurring in the body, and we can also see how much is the stress wave transfer. Okay, so this is overall things that we will try to implement. So from the previous lecture, okay, we summarize like if you remember last lecture, we have talked about the impact event. So impact load is nothing but a sudden application of a force over a very short duration, which causes stress waves to travel throughout the material. Okay, so if you look into force versus time, okay, the impact loading is nothing but the contact force between the two bodies. Okay, if it is an elastic impact, this graph will follow a Gaussian shape. Okay, in day-to-day life, we come across different types of impact event, like when we nail a hammer, when a car crash occurs, or when some sort of missile or projectile hits its target. So, these are very general cases of the impact event. So, impact load occurs in many engineering principles, and since it involves large displacements, high strain rate, plastic deformation, the analysis of this impact event is very complex. And that is how what we will do is that whatever we have learnt in the last slide, we will try to apply those things and get an approximate engineering estimate for the impact scenario. Moving ahead. So, right now what we will do is that we will try to quantify some basic things. Okay. So, one basic phenomena we will try to classify, that is called an impulse. So, the impulse is defined as a product of a force acting on a body in a very short duration of time. Okay. So, using Newton's second law of motion, we can write the equation of the force, and then if this force is acting at a time dt, so using this principle we can calculate the total impulse. Okay. So, what we have done is that we have Newton's equation, second law of motion, and using this second law of motion we have categorized the impulse. Okay. So, impulse we are also categorizing as the net change in the momentum. Okay. Momentum final minus momentum initial is called as the impulse. Okay. So, in impulse we can categorize impulse as the change in momentum. Okay. So, this is the simplest approximation of an impulse, where we call it as the change in momentum. Okay. And simplifying it further, the change in integral of the force time history area is also called an impulse. Okay. So, what happens during an impact event is that an enormous force acts on the body for a very short duration of that time. The impact duration is normally in the range of milliseconds. Okay. So, in this milliseconds a huge amount of force is applied on the body. Okay. So, the entire integral, okay, the area of this very large force acting over a very short time is called as impulse. Okay. So, what happens to the body is that a very large deformation acts on the body. Okay. And this body we say that it has been acted by an impulsive force. Okay. So, the point to remember is this curve, this force time history curve, which can be approximated by an Gaussian curve. Okay. And the area under this curve is called as impulse. Okay. And also we can call impulse as the change in the momentum. Okay. So, using this slide, what we have learnt is that the area under the force time curve is impulse, and the change in the momentum is also impulse. Okay. So, this is the simplest definition of impulse. Moving ahead. So, using the concepts from the classical impact mechanics, okay, we will try to reiterate some of the key concepts. Deformation history in an impact event is considered to be consist of two intervals, approach period and the restitution period. Simply saying, it means that approach period is when the impactor tries to approach the body, stationary or other moving body, makes a contact. This is called the approach period, and when the contact is lost, okay, that is the restitution period. So, approach period extends from instant of contact to the point of maximum deformation. Restitution period starts from the point of maximum deformation to the instant of separation. Okay. So, in case of complete elasticity, this curve is symmetric. It means that the force time history curve will be a Gaussian curve. It is a symmetric curve. In case of partial restoration means some sort of permanent physical deformation has taken place, okay, or it is an partially elastic impact. The initial part was elastic impact and the other part was an plastic impact. So, in that case we obtained a unsymmetric force time curve. So, in case of perfectly plastic impact, the body do not separate, so there is no restitution period. If we look into the graph and if we plot the deformation over the period of time, okay, so that from the start of the event to the maximum deformation, that is called the approach period. Okay. And during the restitution period, meaning from the point of maximum deformation to the point of separation, if it is perfectly elastic, then the deformation is regained, the system behaves as an elastic impact. If the deformation is not 100% regained, then some permanent deformation occurs and the curve is not symmetric. Okay. So, this is a case of perfectly elastic impact, and in the case of a perfectly plastic impact, the body will not separate and there will be no restitution period. Okay. Moving ahead. So, now we will talk about the response to impact loading. So, elastic response. So, now what we will do is that we will model the body using a very simple approximation. Okay. So, the simplest and most conservative model is to assume that the structure remains perfectly elastic after impact. It means that the force versus time as well as deformation versus time graph is symmetric. Okay. So, what we are doing is that we are representing our body using a very simple model. Okay. So, it is a single degree of freedom system which has a spring denoting the stiffness in the body, a mass m, and it is acted by a velocity. Okay. So, this is the simplest representation of a body having a mass and a spring. Okay. So, energy conservation overview. So, the strain energy is stored in the deformation and the kinetic energy is in the energy of the motion, and this two, using the energy conservation principles, they keep on interchanging. Okay. So, let us say that this has been impacted by a force F. Okay. So, the impact force F carried by a spring and its equal and opposite reactions act to slow the mass and compress the spring. Okay, at a maximum distance y max. Okay. So, the kinetic energy in the body will be half mv square. Okay, and the spring energy of in the deformation will be half k y max square. Okay. So, using the energy principle, we can calculate the maximum deformation. Okay. What we are doing is that we are equating the kinetic energy and the spring energy, and using this very first principle, we can calculate the maximum deformation. Okay. So, this was the very simplest single degree of freedom approximation and the calculation of the maximum deformation, okay, in a body. So, continuing from the last slide, the kinetic energy is equated with the spring energy and we calculate the maximum deformation. Okay. So, the spring force is stiffness times the maximum deformation, and that we can write in terms of the stiffness and the energy. Okay. This approach is conservative because it ignores damping. We are not considering the damping that is occurring in the body, we are not considering the friction, and we are not considering any inelastic deformation or any other energy absorption mechanism. Okay. So, this will give us a very conservative estimate, okay, because any type of damping, friction or any type of losses are not being considered here. Okay. So, this approach produces a reasonable result for assessing items such as bumper, where impact is a severe condition and the damage is to be prevented and not simply tolerated. Okay. So, since it is a very conservative analysis, it will give us an answer on the higher side, and for the systems where it is very necessary, it will give us a very good approximation. Okay. So, again elastic response. So, now we will look into the impact on a beam by a dropped mass. Okay. Let us say we have a beam. Okay. Let us say it has hinge and hinge boundary conditions. If you look into the two ends, the boundary conditions are hinge and hinge. Okay. Let us say it has been impacted by a mass and a moving velocity. Okay. And the length of the beam is L. Okay. So, assumptions, we will use the following assumptions. The beam stiffness is same for static and dynamic loading. Okay. It means that the value of the stiffness does not change for the dynamic and the static condition. Okay. So, whatever we are assuming the stiffness for the static condition, we will take the same stiffness. We will ignore the mass of the beam. Okay. The deformation is occurring without energy loss. So, the mass will rebound forever. Okay. So, energy exchange between kinetic energy of the mass and strain energy of the beam takes place. Okay. So, in this case the energy to be absorbed in the incoming kinetic energy produced by the impactor having a weight W and velocity V, plus the additional work done by the weight W acting through the beam deformation. So, the total energy to be absorbed is Ek plus W times Y max, okay, which is nothing but my kinetic energy plus the additional work that the W has to move, okay, when it is acted by the body. Okay. So, this is the total energy imparted by the external object on the system. Okay. Now, we need to balance this energy. Okay. So, this energy will be balanced out by the stiffness of the beam. Okay. So, the energy by the external impactor, okay, that is the kinetic energy in the system, okay, due to the weight W plus the work done by the moving mass, okay, that is Y max. Okay. So, those two energy component will be taken care by the stiffness in the system. So, here we are equating that Ek plus W Y max equals to half K Y max square, meaning Ek is nothing but my kinetic energy of the impactor plus the work done by the impactor when it moves a distance of Y max, okay, and this total has been absorbed by my stiffness in the beam. Okay. So, we equate it, and using this equation we can calculate our maximum deformation. Okay. And maximum deformation we can also write in terms of maximum static deformation. Okay. So, maximum static deformation is nothing but when my weight is kept on the body, weight is kept on the spring, and the amount of movement it takes place. Okay. So, we denote it by Y static, and now what we are doing is that we are writing our maximum dynamic deformation in terms of static deformation plus a coefficient. Okay. So, what has been done here is that the maximum dynamic deformation has been represented in terms of static deformation plus the conditions given by the impactor. Okay. If you look into the box, okay, the components Ek is made up of half W V square, meaning the mass of the impactor times the velocity of the impactor, okay, divided by W YST, the static deformation and the mass of the system. Okay. So, this thing we call it as the dynamic amplification factor, meaning the factor by which a load effects is amplified when we are dealing with a suddenly imposed load, meaning when we are dealing with an impactor, what is the difference between the static deformation and the dynamic deformation. Okay. Dynamic amplification factor is a very neat way to represent the effect of the moving body on the beam. Okay. So, this equation we can use as a design also. Okay. So, now we were dealing with the elastic response, okay, meaning the curve, my curve was my force versus time as well as deformation versus time curve was symmetric. Okay. Now, we will be dealing with the inelastic response, meaning that total recovery has not taken place and there is some inelastic deformation in my body. Okay. So, what we need to do, if we do a proper elastic design, okay, there will be 100% recovery in the deformation, but on the other hand what will happen is that my design will become very heavy. Okay. It will be heavy and durable, but the cost associated with that design will also be a lot. Okay. So, always in design we have to maintain this balance. Okay. The balancing act has to be done where the cost of the heavy design, okay, has to be somehow balanced with the response that we are seeking. Okay. If we do a very heavy design, the cost will be more, and if we do a very light design, the deformation will be more. Okay. So, we will have to establish a parity between this deformation and the plastic deformation and the cost associated with that. Okay. So, economics often dictates that the repair of the structure subject to infrequent damage may be cheaper than producing and using a structure that responds elastically. Okay. So, this is the guideline principle used in the repair of the systems. Okay. So, what we will do is that we will allow some plastic deformation in my structure. So, idealized, so the given curve is an idealized elastic plastic behavior. If you look into the curve, you will see that if my system is behaving in an elastic way, what is going to happen? If I keep my system in the elastic phase only, the force demand is more and more. Okay. So, what I can do is that I can allow some plastic deformation, okay, and then it will bring down my force demand. Okay. So, that way I can optimize my structure while allowing some plastic deformation. So, this is the principle that is used normally in the design process, where some plastic deformation is allowed to achieve an economical structure. Okay. And the ratio of Y max to YU, meaning the total plastic deformation to the elastic deformation, is also sometimes called as ductility. Okay. So, the amount of ductility required, okay, will be dictated by the economics in the structure, or how economically viable we are trying to make our structure. Okay. So, this is the guiding principle that we need to understand. Moving ahead. So, the strain energy is simply the area under the curve. Okay. So, what we will do is that we will equate the kinetic energy of the impact and the strain energy, and then we can calculate the Y max required. Okay. So, the displacement Y max is limited in practice by the ability of the structure to absorb plastic deformation without becoming unstable. Okay. And ductility is nothing but my ratio of Y max divided by Y elastic. Okay. So, what we will do is that we will equate the work done and the energy absorbed to calculate how much is my required forces. Okay. So, as a general rule, ductility factors exceeding 10 are associated with very heavy damage. Okay. If ductility is 10, it means that the allowable plastic deformation, the value of the allowable plastic deformation is 10 times the value of the elastic deformation. It means that my structure has undergone a large deformation. Okay. It means that my structure has sustained a very heavy damage. Okay. So, this is some sort of thumb rule that we normally establish. So, what we try to do is that we try to apply a ductility factor below 5. Okay. So, below 5 we say that it produces a tolerable damage. Okay. And it will probably allow the structure to continue in use whenever the repair are being undertaken. Okay. So, in general guiding principle, a ductility factor of 3 to 5 is normally adopted, okay, for a repairable structure. Okay. It allows for economical design also, and the structure is again able to function when the repairs are being carried out. Okay. So, what we have done is that we have tried to establish a parity between the cost of the structure and the total damage that it can sustain. So, now we have looked into the elastic response, we have looked into the plastic response. Now, we will try to go deeper here, and we will try to see the contact mechanics, okay, how the deformation happens when the two bodies are in contact, what are the contact forces, and so on and so forth. So, contact mechanics. So, during an impact, when two bodies come into sudden contact, the transfer of the momentum and energy takes place. Okay. This leads to a localized deformation and stress generation at the contact interface. Okay. So, as we have seen earlier, in the first part, what we did was we simplified the impact problem using the basic principles, and we tried to estimate. Okay. We estimated the maximum deformation that is occurring in the body. Then again, now we are trying to put some more complexity, we are trying to add complexity, and we are trying to analyze the impact phenomena. So, now what we are trying to do is that we are trying to look into the forces developed at the contact interface. Okay. So, the parameters associated with the contact mechanics are deformation, that is change in shape of the body during a contact event, the contact force, that is the force applied between the bodies during a contact, duration, that is the length of the time of contact, and contact area, that is how much area of the two bodies are in, how much the two bodies touch each other. Okay. So, this four parameters we will try to estimate: the deformation, the contact force, the duration, and the contact area. So, contact phenomena. The contact phenomena has been studied by a lot of people, and the most prevalent theory was developed by Heinrich Hertz in 1882. So, Hertzian contact theory is the most accepted theory, and most of the principles or examples or applications are based on the Hertz contact law. So, what it does, Hertzian contact theory or Hertz law gives us a mathematical way to predict what happens when two curved surfaces press together without friction and without permanent deformation. Okay. That is, they bounce back to their original shape, that is purely elastic contact. Okay. So, we will look into the assumptions of the Hertz theory. Non-conforming bodies, okay, bodies that touch at a point or line before loading. Okay. So, the bodies are non-conforming. The material behavior is elastic. Okay. It means that the material returned to their original shape after deformation. Small deformations, so the deformations are minimal under the loading. The surfaces are smooth, surfaces with minimal friction, and the contact area is small. So, the contact area is small relative to the inherent size of the body. Okay. So, these are the 5 assumptions of the Hertz contact theory. Okay. So, Hertz contact theory can be expressed in terms of this equation. Okay. So, this equations provide a relationship between the contact force and the displacement that is occurring in the body between the two elastic bodies. Okay. So, the contact force is the force developed at the interface between two bodies, okay, and that is related to the deformation undergone by the body. Okay. The approximations, okay, or the mathematical relationship between the two bodies while used to develop this, the Hertz contact theory is been given by these 3 equations, okay, where K naught is the stiffness of the body. So, K naught is related to the material properties, okay, where mu1 and mu2 are the Poisson's ratio of the two materials, and E1 and E2 are the elastic moduli. Okay. So, in the first equation, what we are trying to do is that we are trying to relate the stiffness between the two bodies with their inherent material properties. Okay. 1 over r star. So, r star is nothing but the radius of the two bodies. So, in general, we are trying to get an idea of the relationship between the radius of the two curved bodies. Okay. And A is denoted by the maximum contact radius, where the material properties and the curve of the body is used to calculate the maximum contact radius. So, we will try to use this 3 relationship in order to calculate the force displacement relationship, which is our Hertz law. So, what happens if we try to plot this thing? Okay. The area under the force deformation curve represent the strain energy absorbed. Okay. So, we can simply write the strain energy as the integral or the area over this contact force. Okay. So, the strain energy we can express in terms of the relative stiffness and the deformation that is occurring in the body. Okay. The kinetic energy loss during the approach or the loading phase is expressed by Ek equals to the kinetic energy equals to half m star Vr square, okay, where m is the effective mass of the system, okay, that is the total mass engaged of the two bodies, okay, and Vr is nothing but the relative speed. Okay. So, what we see is that we have a resistance deflection plot for the local deformation that is occurring in the body. So, equating the strain and the kinetic energy gives the maximum relative movement and the peak force of impact. Okay. We can calculate the maximum relative movement denoted by delta, and we can also calculate the peak force of impact. Okay. So, using the Hertz contact law, what we are able to do is that we can calculate the maximum relative movement that is occurring between the two bodies and the force at the point of contact we can also calculate. Okay. And these things are given in terms of the effective mass, the relative velocity and the stiffness between the two bodies. Okay. So, I will stop here. Thank you.